Wow.
What this camera is using right now, we get fingerprint detail.
Fingerprint. So hold on, you built this system?
Yeah.
So I'm here with Nasir. Thank you very much for having us today.
Absolutely.
Now, what's your role here?
I'm principal engineer for the Advanced Design Automation Metrology Lab at CCAT.
Now, that's a very specialized role. How did you get into that? What got you into this kind of line of work?
Well, really the mission here at CCAT is to help manufacturing companies advance by using the latest and greatest technologies so they can streamline processes, and that's what really drove me to CCAT. It's a place that I can come to help companies implement, well, first understand and then implement advanced technologies, and that's my passion. It's all about learning what's new, learning what could be, and then actually seeing it getting there and being used. So that was kind of the passion behind coming here.
And have you always had that interest, since a young age, in advanced technology? Is that what kind of got you into that early on, or?
Yeah, I think it started, my father's an electrical engineer.
Cool.
My grandfather was an engineer and his father was an engineer, so I guess I have it built into me.
Right.
It was always, my subject matters of interest in school were physics and math. I just loved it, and nobody understood why. I have 4 younger brothers, they'd all look at me like you're crazy. But yeah, so I think I have, the interest is there.
And it was a natural progression into, obviously, a place that does such cutting edge work like this.
Absolutely.
So what kind of stuff are you guys focusing on here today? What's exciting?
So we've got a number of things going on. We've got a couple of programs that are focused on helping companies understand Industry 4.0 technologies. So one of the first pieces of equipment that we can see right in front of us is a collaborative robot. What's neat about this is the collaborative part is that this robot can do functions and not need a safety barrier around it. Because it has the intelligence built in and the sensors built in where when it does something and it comes in contact with the person, it'll stop.
Because generally when you build a robot cell,
Yeah.
you need to have this thing fully caged in, or at least with light curtains, and
Yep.
it's a big expense.
Exactly. That whole expense is taken away by this. They're a little bit slower, but that's fine. It enables the collaborative mode. What we're actually setting up here today, you see the scanner here. You see a blade here. This is a turbine tip repair application where normally if you have wear on the blade, you can weld down some extra material or use additive manufacturing to weld down some or add some additional material there. And then you would typically go back and grind it down with a grinder or some kind of a machining process. Here we're showing the automation of it. The robot picks up the part. It'll go to a welder, which we'll set up. It'll weld on a bead, and then it'll bring it over to the scanner, scan to make sure we have enough material. Then it'll go through a grinding process and bring it back over, and basically just do this verification check.
Wow.
And it'll all be set up in a way where it's automatically figuring out when that blade is back down to what it was supposed to be.
So literally you put in, a damaged blade, you put it in, and then
Yep.
this thing does the rest. You come back X number of hours later,
Yep.
and you have a finished, repaired blade ready to go.
This is a kind of a setup of exactly what you described. We want to show companies how you can use a collaborative robot. It's one thing to just show it and then to actually demonstrate the use case. I think that's what hits home to companies and when they apply it to their
Because as a guy, I'm a machinist, I have a machine shop. When I think of cobots, I think of something loading and unloading a machine. I don't think of something literally operating on its own in collaboration. Is this sensor something that you guys have developed in partnership with somebody, or did you guys do this yourself? Or?
No, this is all, it was developed outside of CCAT, but it's all a CCAT product that companies can get from here. It's a structure light scanner, so it's a non-contact way of measuring a part. It's perfect for this because it's quick. It's literally just like taking an image. You get the 3D information, and it's enough information for the robot to make a decision. So.
And with this kind of stuff, because you're dealing with 3D printed parts, do you guys collaborate with the other side in the actual additive lab? As much as there a collaborative effort between the two sides of this?
Absolutely, and you'll see more when we walk over to the CT scanner.
Excellent.
Yeah.
not sure what I'm looking at, but it is the size of a room.
Yeah. So this is our ATO scan box. It is a structural light scanner. You see the red component there that's shining that blue light on the floor. I'm going to go ahead and just run it real quick so you can see how it
Absolutely.
works.
I'm going to step over here so I can see it from over this way.
What the system does is it uses light, just like the scanner that I showed you a minute ago. It uses light, it flashes it on the part. It's basically capturing 3D information on that part.
Right,
and
so that's shooting and receiving at the same time.
Exactly. And it's all the while, it's building up a model here on the screen of the actual part in 3D. So you can see here, you've got the actual part there being constructed. And what we can do with this information is, because now we've captured a physical object in digital form, we can compare it against the original design, which is the CAD file. And we can very quickly see where that part is in tolerance, out of tolerance. The purpose of showing this particular system, the way it's set up, is to show full automation in inspection.
Right.
So this is typically somewhere where a manufacturing company might be a little slow. Manufacturing might be fast, inspection might be a little slower.
For sure.
It might be a manual process. It depends on what the company's doing. But this is kind of they can come in, they can see very quickly, within a matter of a couple minutes, I've captured the part, I've inspected it, and we're done.
That started and finished like that.
Exactly. Yep.
Now, when that information's in there, that builds an STL file. I'm sure you can export it in any way you want.
Exactly. Yep.
And you could keep those as your inspection records if they're serialized.
Yep.
For if anything ever goes wrong, or you need to do a quality assurance report or anything like that. That's all in the computer now.
Exactly.
What kind of companies and what kind of industries are you seeing shift over to using this kind of inspection equipment?
We primarily deal with aerospace, but obviously with the marine and maritime, there's automotive uses this extensively, and medical as well. But really, this is applicable to all industries. I mean, when we walk over to the other scanner, I'll show you some of the other applications there. We've seen artists, architects, even computer graphics. This kind of technology is used to capture reality, and it captures it in very high resolution. And so when you have that digital twin, you can use it in a digital environment however you want.
Which is really helpful.
Yeah.
When it comes to complex parts like this, I've occasionally had to reverse engineer parts, and trying to make sure you're actually getting that part into CAD and CAM can be very difficult, if not impossible, because some features are very difficult to measure.
Yep.
So by using something like this, I could literally take a part I buy off the shelf, slap it down, and within a minute and a half, I have full 3D geometry.
Yep, exactly.
Incredible, absolutely incredible.
I'll bring you over to this other machine that we have here. What we saw there was a structural light scanning system that scans a part. It grabs information on the surface. This is a system, it's a X-ray machine and CT scanner. So it's got the ability for us to take digital radiographs. So we can very quickly see images like this and do quick analysis on issues that might arise in the part. This is an example of a lens system, so you can see the various lenses within this assembly. Same thing here, this is a casting, so we can very quickly look through the part, see if we see any cracks there. But at the same time, this system has CT scanning capabilities as well. So if you look inside the machine, on the right side there's a tube, that's a microfocus tube. On the left side there's a panel, that's the actual detector.
Oh wow. Okay.
And the CT portion of it is when you rotate the part and grab a bunch of x-rays, and that gets reconstructed into a volume file. And from what we do from here, we can visualize that data here on the screen. This is an example of a camera lens that we scanned. There was an issue with it. And what's nice about CT scanning is because we have the full volume information of all the surfaces inside and outside, we can start to cut through the part to see if there's any issues within. Or we can eliminate materials that we don't necessarily want in the way.
Oh, really?
So we can see inside. So as an example here,
this
is a particular cutout. You can cut through the part and very quickly see if there's any issues within.
It's just like water jetting it right in half, except you just
Exactly.
have a digital version of that.
Exactly. It's all non-destructive. Here's an instance where we actually got rid of the aluminum housing, and we're just looking at the lens system along with the iris and the locking mechanism. We're also seeing some of the screws. So essentially, we're taking away some of the less dense material and seeing the more dense.
And how difficult is that once you've captured I know the system had to be built and that was very difficult, but now that at this stage, after you do that, how difficult is that to pull out different materials once you have that file?
It's as simple as a slider bar.
Really?
Yep.
Wow.
It's pretty straightforward. In this case, we were looking visually why this iris was not closing, and you can see the iris locking mechanism jammed into the wrong portion of that. And so that's what we're left with there. But so the power of this technology is really, especially working with the Atom Lab over on the other side. They'll build a lot of test coupons out of additive, and they'll use specific machine parameters to come up with that test coupon. We'll go ahead and CT scan it, and we'll see, are there any voids within the part? Are there foreign objects included in there, like pieces of the powder that were not the original material?
Right.
And we can very quickly see an overview of that. Where we get more into the analysis is on this computer. We use a piece of software called Volume Graphics, and in here, this is an example of an additive part. And what we're picking up on here are all the voids, all of the porosity within the material.
Oh, I see.
And so these particular projections are cut-throughs of this part. So we're seeing the 2D views here, but here's the full 3D reconstruction. We can tilt and rotate it around.
Because a lot of those you may not be able to see at all from the outside.
Exactly. I actually have it here. So we can map all of the issues that are contained within the part in 3D space. We can zoom in on it, and there's a particular area here where the flange meets the cylinder body. You can see it's colorized red because you have a large number of porosity over there.
And for something that may be in like a high pressure application or a rocketry application, that's a point of failure, potentially.
Exactly.
So you need to know it, and you may not know it's there.
Yep.
That helps you identify it before it goes on to the spaceship, airplane, whatever it may be.
Exactly. So traditional methods is to cut through the part and do a microscopy, do like an image of it on a microscope and try and find the pores there. The issue there is that depending on where you cut, how many number of cuts you take, you might not see everything. With non-destructive testing, you get all the information right away. The neat thing here is once this defect tab comes up, you'll see a bunch of rows. Each one of those rows is indicating a void.
Oh, wow.
And it has a lot of information on that void. It has the sphericity of it, it's got the diameter, the volume, where it is in XYZ space within the part, and some other metadata that's attached to that.
So literally it gives every single issue that could exist, does exist with this part in an easy to read format.
Exactly. We can also do this, I'm showing additive. This is a very good technology for composite parts.
Right.
So we can see fiber orientation. We can see any disc bonds, delaminations. We can pick up on a lot of different kinds of problems that are contained within composite parts.
Right.
So.
Which is very difficult to find otherwise.
Exactly. This is another structural light scanning system. You can see that it's running now. It's projecting a line pattern on the surface of the part. A camera is receiving that pattern as it's being deformed on the surface. And so because there's a difference in the signal of what's going out versus what's coming back in, the surface topology is causing that, and the system is able to take that information and calculate a 3D surface.
Just from that light being put on there, it can tell.
Yep.
Wow.
Now it is line of sight, so whatever it's casting a light on, it's able to capture. Anything that's in shadow, it's not going to see.
Right.
If you have a very deep hole, it's most likely not going to get all the way down into the hole. But for the surfaces it does see, you can see it very quickly as we were standing there forming a model of that part.
Now, what is the resolution on something like that? Are we talking 5 thou, 1 thou?
You can actually get down to 2.5 microns on it.
Oh, wow.
Yeah, some of the examples here, I'll show you. The other applications, we have, here's an application for museums where you're actually capturing artifacts that are priceless.
Absolutely.
They have a lot of worth to them. They want to do analysis on it, but they don't want to touch it because it's a very fragile surface. You don't want to you don't want to handle it.
Because it's completely contact free.
It's completely contact free, and that's the best part. It can capture color information, so you can see the 3D geometry, the color mapped on it. That's the actual scanning while it was happening. You can capture people for CGI.
Oh, wow.
You can. This is some other color scanning applications. Resolution-wise, this is probably a good image to show. With just 3 megapixel, what this camera is using right now, we get fingerprint detail.
Fingerprint.
Now, we can get up to 16 megapixels, so we can change that camera out to a much higher resolution, and that hopefully gives you a visual in your mind of how high resolution
you can see the DNA in my fingers, just about.
Exactly. I might show you this one other image that might help also with the resolution. Is you can see these smaller parts and some of the detail that's involved. Here's a small turbine tip repair. That's exactly what I described on the other side. So we're capturing that information. But you can see the reference there as a dime.
Tiny.
It's tiny. Here's some cooling channels that are laser drilled into parts, 1 millimeter on this one.
And you can literally see the slag on them.
Exactly. Some coins. Another museum application is scanning insects for studying. And then there's other applications for health and medical. This is one for creating prosthetics. So this is a multi-scanner hand scanner where it's a process where if a person's missing, if they had an amputation on a finger or a thumb or a leg, what you want to do is match the other side as evenly as you can, and you want to do that consistently over time because things change, dimensions change, and to quickly capture the geometry of the unaffected limb, you can mirror copy that over because you have an exact replica.
And especially using things like additive manufacturing in order to produce that. You got an accurate solution and a quick solution.
It does a world of difference to the patient who has a form-fitting prosthetic because they can now concentrate on the task at hand rather than the discomfort that prosthetic is giving. So that was a very cool project that we did.
So hold on, you built this system?
So this system here, the reason why we built it, this was back in 2013, was to help alleviate the cost barrier. There was 2 issues. One, it's the systems at that time were not certified as CMMs are and some other measurement equipment. They were somewhat expensive to onboard for the small companies, and they were somewhat restricted in the kinds of parts that they can scan. So in order to come up with a solution where a small company could be in a position to actually onboard, try out the technology, and actually use it in process, was to come up with a system that used off-the-shelf technology. So this is a regular machine vision camera, a projector you'd use for a PowerPoint presentation.
Oh, really?
Yeah, and the system, the actual brains behind the solution is the software, where you can take these off-the-shelf components, plug them into your computer, and the software is able to calibrate it to be able to be used as a structural scanning system.
See, I thought this was some kind of specialized rig that was developed. This is, like you said, you could go buy this at Best Buy, go buy that at Best Buy, or wherever you buy fine electronics. That's incredible. Now, sorry, how do I phrase this? When it comes to companies putting these on the floor, what companies are you seeing do this? Are manufacturers getting on board with this versus CMM?
Yeah, I mean, the accuracies that you can achieve with this are down to about 3/10,000ths of an inch. And if you go bigger in the field of view, you're getting closer to about 1,000. So in contrast to contact type measuring systems like a CMM, it's not going to be as accurate. CMMs are sub-micron accurate. But in applications where you don't need that kind of accuracy, you need a real quick capture of an object, for example, castings. Manufacturers will get castings in and they machine products out of that casting. You want to make sure you have enough positive material. That's that's kind of a no-brainer.
Absolutely.
Something that's you can onboard for a couple $1,000, place it on site, scan the casting, make sure you have positive material, put it on the machine is great. Medical devices are a great one as well. Any kind of component, for example, marine maritime, something for that goes on a submarine, or a bracket for an aircraft, or things of that nature. Because you saw the size range, there's no size part that you can't scan with this. It's just the practicality of how many scans you're going to take. We've scanned cars.
Oh, wow.
We've scanned motorcycles. We've scanned a helicopter blade. And we've also scanned, as you saw,
Tiny
parts
little
that fit
things.
within an inch. So it's very flexible. It's just like, it's very similar to, if you think of the applications of a camera. You can use a camera anywhere.
Exactly.
And this is just a 3D camera. So the possibilities are quite vast.
That was great. Thank you so much for your time. That was amazing.
Yeah.
So there you have it, guys. Thank you very much to the people at CCAT for showing us everything that they're doing in there. This is really and truly the cutting, bleeding edge of where the trade is going. For me anyway, it was super interesting to see not only new machines, but the new applications of them. 3D metal printing has been around for a minute, but seeing some of the ways they're pushing the envelope and what those applications are gonna be, especially with like the ferric and non-ferric metal combinations, the advances in NDT testing, it's going to take a while to trickle down, as a lot of these technologies do, to where it's going to be usable at a ground level for a lot of shops. But getting to see where these technologies are going and how they're going to affect our jobs moving forward is super, super interesting. I hope you guys found that as interesting as I did. Thank you very much for watching. Thank you very much to CCAT, and you take care.